So last time we were looking at sequences, right? Patterns of numbers, and today we're going to extend that idea to something called series, and specifically talking about when series converge or diverge. So the first thing that we need is we need a definition of what we mean by series. So if A sub n is an infinite sequence, then the summation from n equal 1 to infinity of A sub n would be A1 plus A2 plus A3. And we keep going, and since it says to infinity, we keep going forever, right? It does not have an end to it. This is called an infinite series. Or simply a series. The numbers A1, A2, and so on are the terms of the series. Okay, so a series is just a summation of a sequence. And if we were to sort of stop somewhere in the middle of the sequence that continues forever and we're adding up, right, we would actually get something called an nth partial sum. So for the series, so the nth partial sum is Sn is A1 plus A2, and we would stop at An. So if we stop somewhere, we have a partial sequence or a partial series. I'm still not saying the right word. A partial sum, that's the one I want. A partial sum of our series if we stop somewhere in the middle. So if it said S sub 3, we would stop with 3 terms. If we said S sub 6, we'd stop with 6 terms. And if we take a look at the sequence that creates by finding what S1 is and what S2 is and what S3 is, so that is a sequence itself. So if the sequence of partial sums converges to S, then the series that goes to infinity will also converge. The limit S is called the sum of the series. And S would equal A1 plus A2 all the way on forever, right? We keep adding those together and we get the sum of our series. This equals the summation from n equal to 1 up to infinity of a sub n. And likewise, if the sequence Sn diverges, so the sequence of partial sums diverges, the series diverges. So in this section of material, we will spend the majority of our time doing two things. So we'll spend most of our time in the rest of the chapter answering these two questions. One, does the series converge or diverge? And then number two, when it does converge, what's its sum? So when a series converges, what is its sum? And what you're going to see in the rest of the chapter is like one test after another test after another test, examining different kinds of series that sort of fit in these categories to make those decisions. So some series will look a lot like, this particular type of a test, and others won't look anything like it, and it will be unusable. And so again, this is a lot like Chapter 8 when you looked for integration techniques back in Calc 2, where you're looking at all these different techniques. Sometimes you have more than one technique you can use, and sometimes there's not. There is specifically one technique, and that's it. You have to go that route. So we're going to see that happening in the rest of this section. So some sequences, this is easy to work with, and it's easy to answer for, and some sequences, it's hard. And also, finding whether something converges or diverges does not necessarily mean you can always find what the sum is. It's sometimes possible to do one and not to do number two. You don't have to have both things going on at the same time. The first sequence we're going to take a look at is a really simple sequence, and you have seen it before. So we're going to define it like this: the summation from n equals 0. Notice it does start at n equals 0 on this particular sequence. If it starts somewhere else but has the following pattern, we just have to make adjustments, and we'll see that happen, I think, today on an adjustment. But this sequence is a times r to the n. So if we were to put in n equal to 0, we would just get a. If we were to put in n equal to 1, we get a times r. If n equals to 2, it's a times r squared. And we continue with increasing our powers on r. And it continues on indefinitely, of course. And this is a geometric sequence. And I said sequence and I meant series. I'm sorry, series. With ratio r. And the only thing that r cannot equal is 0. If r were to equal 0, everything after the first term a would cancel out because it would be multiplying by 0 or a power of 0. It wouldn't be a very exciting summation. Okay? So as long as r is not 0, it will work, which means r can be positive, it can be negative, it can be fractions, it can be decimals, it could be pi, it could be anything. We're working in the real number system for calculus, so that's not the case. Yes, calculus on real numbers only. Yeah. Thanks for asking. It's a wonderful question. All right, so real numbers. All right, so when does this sequence converge and diverge? Because that's what we're trying to answer when we find out we have a sequence that has a certain pattern. And here is actually what we find. And you've probably seen this sequence possibly in like an Algebra 2 class, maybe a geometry class in high school. once you see what I show you next, you'll be like, oh yeah, I think I recognize this portion of it. So at least you've seen a portion. So it looks something like this. So this is theorem 9.6, and it talks about when things converge. So a geometric series with ratio R diverges when the absolute value of R is greater than or equal to 1. If the values between 0 and 1, strictly the ratio, then the series converges to the sum so for the summation from n equal 0 to infinity of a r to the n, and it's a over 1 minus r. Does that a over 1 minus r look familiar? It usually pops up somewhere in high school when you're looking at sequences and series that are terminating, like they stop instead of being necessarily infinite. And you kind of throw this one in there and say, oh, there's this one lovely infinite series that has this special form, and it has this equation. The tendency sometimes is to forget that this equation hinges upon the fact that r is between 0 and 1. So if r is bigger than 1, this equation, right, that tells us a over 1 minus r, while you could plug r in there and you would get a number out of that, it is not going to be a number that means that that's what it converges to, because it doesn't converge, it diverges. Okay? So we can only use this formula or this equation that says that it's a over 1 minus r if r is between 0 and 1. So we're going to do an example. We're going to find the sum of the convergent series. So this example, they're actually telling you it converges off the, right off the bat. But as we look at it, we should be able to say, yeah, we'd have known that ourselves. So we're going to go from k equals 0 to infinity of 1/2 times negative 1/3 to the k. So the first thing I'd like for us to note together is, why does this converge? It doesn't ask us this in this problem, but I want us to make sure we're aware of it. Why is it converging?
Because any fraction or number between 0 and 1 will eventually, the limit of would equal.
Okay, so I think you're going a little further than you need to.
Yeah. Oh.
Just rely back on the previous theorem. Is this geometric?
Yeah.
Yes. And what do we know about the ratio of this geometric series? What is it in this problem?
It's less than 1 and greater than 0.
Okay, what is the value?
1/3.
1/3. Okay. So the negative, and it's negative 1/3 actually, right? So the negative 1/3 here, so the absolute value of negative 1/3 is between 0 and 1, right? So because this absolute value is between 0 and 1, it converges. That's how we know it converges. It's geometric, and it has the ratio that fits into this constraint. Because that's the case, we're able to actually figure out what it converges to. So the first number in the series is going to be what happens when I plug in k equals 0. So what happens when I plug in k equal to 0? You get the 1/2 that's in front, right? Now, technically, you could also say, well, doesn't it just automatically equal the 1/2 because it's in the place where the a is? It does here because k starts at 0. If k did not start at 0, we could still employ this strategy. Like, let's say k started at 3. If we put 3 in, we would find the first term, and that would be my a value. So even if k or n or whatever variable you're using is not at the bottom starting at 0, we can still employ that idea. So we've got 1/2 for a over 1 minus r, and it is 1 minus negative 1/3. So it's not the absolute value, right? It's not the 1/3. So we do want to be careful about that. We're just doing the absolute value to decide if it converges or not. So on top I have 1/2. On bottom I have 4/3. Yeah? What will this simplify to? 3/8. Whoops. The right number in the right place, 3/8. So our sequence converges. Our sequence has a summation, our series has a summation value 3/8, and we're done. Is that all right? All right, so what would need to be different in this sequence? We'll flip back to it. What would need to be different in this sequence in order for us to have a sequence that diverged?
R would have to be greater than 1 or less than -1.
Yeah, so like the negative 1/3 would have to be a different number, right? Can you give me an example of a number in the place of the negative 1/3 that would make this diverge? 2? What else? 3? We can use fractions and decimals too, though, right? There's nothing special about whole numbers. And we can do negatives also, like Jubal mentioned. It doesn't have to just be positive. So we could say something like negative 7.2, yeah? And it would also diverge. Okay, our next type of a series that we're going to take a look at is a little bit more complicated, and you probably haven't seen it before, probably. It is a special name. It's called a telescoping, or it's sometimes called a collapsing sum. And what this is, oops, I don't know why I put that there. Oh, yeah, I did. Okay, this is a type. That's what's wrong. Of series where partial sums are used and terms cancel, hence collapse. So the terms cancel out. And I want to show you how this works with an example, because it sounds great, like things are going to cancel out. That sounds nice. Sure enough, if things cancel out, surely it's going to, converge. That sort of makes sense. But let me show you how it works. So here's our example. We're going to find the sum of the convergent series. All right, so on the last one, that is the geometric series, the sort of red flagging, features of this is that I have a power, right? A power of r, right? My index that's increasing each time is a exponent on a ratio. The ratio has certain features that just tells if this collapses or if this diverges. With a telescoping series, what we end up having is what looks like a rational function. And there are two pieces in the denominator that are multiplied together that look very similar. So the one I'm going to use is the classic example, which is k and k plus 1. But it doesn't have to be k and k plus 1. It could have been k and k plus 3. Okay, so there's nothing special about it being k plus 1. This is just an example of one that would do this. We're going to start from k equal 1 to infinity. I don't want it to start at k equals 0 on this one. That would not be good. I've got a denominator that would be 0. So k equal 1 to infinity is what is happening here. All right, so what we're going to do on this one is we're going to do something called partial fractions. Do you remember partial fractions from Calc 2? So interestingly enough, whenever I teach Calc 2, I talk about the fact that partial fractions are really not a Calc 2 concept. They're actually a college algebra concept. But they're typically not taught in college algebra because they're so far along in the book you never get to them, right? Like one of those things. And they're never used until Calc 2. And the majority of the students who take college algebra are never going to get to Calc 2. So it's one of those topics that's sort of, omitted because we don't need it yet. So partial fractions means taking a fraction that's multiplied together in fractional pieces, right? These two factored pieces, and separating it out into two separate fractions. So our goal is to create a fraction that's over k and a fraction that's over k plus 1. Okay, that's what partial fractions does. So I'm not going to continue my summation right now. We're just going to do the partial fraction part of it over here on the left-hand side. So this partial fraction decomposition is going to equal 1 over k times k plus 1 when we're done. And what we do is we look at the denominator. If the denominator is linear, right, so k and k plus 1, or you would have seen x and x plus 1 if you were in Calc 2, those are linear terms. And so we just use constants on top, a and b. If we had a denominator portion that said like k squared plus 1, we would have a numerator that needed to be linear. It has to be 1 degree less. So a and b are constants. K here is our variable that's incrementing. And what we want to do is we want to sort of have these written as the two separate fractions, and then we want to merge them back together to compare them with the merged fraction on the left-hand side. So we get a common denominator, and a common denominator means I'm going to multiply the a by k plus 1, and I'm going to multiply my b by k, and then they will have the same denominator, which is k times k plus 1. Okay, does that look okay so far? Addition in between. Okay, since the denominators match, right? All I have to consider now is that the numerators need to. So this first numerator is ak plus a, and the second one is bk. And this has to equal the number 1. Well, there's two types of values in the expression that's on the right. There's terms that are multiplied by k, and there's terms that aren't. So we have our terms that are not multiplied by k. There are constants. I'm going to use the pound sign meaning number, not meaning hashtag. Number, okay? And then I'm going to use the k for my variable terms. So the terms that have just a number are really just a. That's the only one that there is. And the terms that have a k in them are a, k, and b, k. Yes? Now, the reality is that right here it says that this a is the only one that doesn't have a multiplication factor by k, so it has to equal 1 because it has to equal the constant that's on the other side. So this a will in fact equal 1. It also means that the k terms can't actually be there because I'm not supposed to, they can't have any value. They don't have any value on the left-hand side, right? There are 0 k's. If I wanted to write in, I could say that. This is 0k. It's 0k plus 1. So this ak and this bk have to actually equal 0k. That is not okay. It looks like okay, but it's a 0k. All right, so this is 0 times k. So what does that actually mean? It has to mean that the a plus the b has to equal 0 in order for this to balance out. And I know that a is 1, right? That's what I just found out a moment ago. So what will b have to equal? Negative 1. So I reasoned through this by comparing it to the values that I have in the original starting, compiled or composed together rational fraction. So what I can do then is I can take this piece up here and I can rewrite it. The sum from k equal 1 to infinity of 1 over k minus 1 over k plus 1. Or you could say plus a negative 1 over k plus 1. Okay, is that all right so far? Why? Why would I want it to be written that way? Well, let's actually put in k equal to 1 and k equal to 2 and k equal to 3. And I think you'll see why this particular form of it is more friendly. If I put in k equal to 1, I have 1 over 1 minus 1 over 2, right? That's if k is equal to 1. What happens if I let k equal to 2? What do I get?
1 half minus 1/3.
1 half minus 1/3. And what if k equal to 3? 1/3 minus 1/4. And this pattern continues, yes? Let me put a dot, dot, dot at the end here. But do you notice right here what happens? Cancels out. It collapses, right? There's a negative 1/2 and there's a positive 1/2. And because this one is k and k plus 1 in the denominators, they're occurring right after each other. So if I'd had like k and k plus 3, like I mentioned a minute ago, they wouldn't necessarily show up that quickly as repeating and collapsing, but they would eventually if you wrote out enough terms. So yeah, I compare these up, and they will keep pairing up indefinitely. And the only thing that didn't get paired up is the one at the beginning, right? So this series is actually converging to the value of 1 because everything else collapses. Pretty cool, right? It's a collapsing series. So clearly that doesn't happen all the time. But when it happens, it's very friendly. All right, I want to show you an interesting application of these ideas that you might not have connected with it in the past, though you've seen it before. So our first directions are that we're going to write the repeating decimal as a geometric series. And then the second thing we're going to do is that we're going to write it as the ratio of two integers. And the value that we're going to start with in our example is actually going to be 0.36 repeating. Okay, so the first thing I'm going to do is I'm just going to write out some of the terms or some of the expansion of this repeating decimal. It would be like this, right? This is the repeating decimal in sort of expanded form. All right, so let's take a look. If I were to consider just the first 3 6 right there, what decimal place location does the 6 end in?
Hundredths.
The hundredths. So as a fraction, this would be 36 over 100. That makes sense to everyone? We're going to do the same thing for the next two values, the next 3 6 here. It's another 3 6, but now it's over what? 10,000. It's the 10,000s place. If I go to the next 3 6, we'll just do one more of them for now. What location is it in? It is the millionths. Like so. And of course it continues. So why in the world would we say that this looks like a geometric sequence? Well, a sequence in a series. Well, because it looks like all that's happening every time is that the numerator stays the same, right? It's staying as 3 6. But what am I multiplying the denominator by to get to the next denominator? 100. So if I keep multiplying by 1 over 100, that would be the R value, a common ratio that gets me to the next value in the series that I'm adding together. So written as a series, this would be the summation from k equal 1, or you can use n if you wish, k equal 1 to infinity. The 36 stays the same, and the denominator is 100 k, like to the k. Or alternately, if you wished to write it, you could write this as the summation from k equal 1 to infinity of the 36th, and then you could write 1 over 100 to the k if you prefer. It looks a little bit more like the description that we had, the pattern of it, on the other screen. Does that make sense? Okay, so if that's going to be our geometric sequence or series, it doesn't quite have the right form. It actually starts at k equal 1 to infinity, and a geometric sequence is supposed to start at k equals 0, right? And I mentioned earlier how we can sort of make amends for that. We simply plug in what happens at k equal 1, and in fact we know that because we've already written it out. When k is equal to 1, I have the 36 over 100, right? So if instead we wanted this to start at k equal to 0, and you may be forced to do so, especially like in a WebAssign, what we would do instead is this would be k equals 0 to 100, and my first term would be 36 over 100, because that's what happened when I put in the first term k equal 1 before, and I still then would have 1 over 100 to the k, because the common ratio is the same. I'm just resetting it at k equals 0, and I'm writing the first term that I would have had in before. So this is like the first step of this problem. The second step says to turn it into a ratio of two integers. What that's asking is, what does it converge to? Okay, so there's other ways to find what this converges to. In fact, I teach this in my one of my elementary ed classes from a very different perspective. But given where we are, we have a very powerful tool at knowing when a sequence converges, what it will converge to when it's geometric. What is their common ratio here? 1 over 100. And 1 over 100 is definitely between 0 and 1, right? So it's definitely going to converge, which means that I can utilize the formula 1 over a over 1 minus r to figure out what it converges to. Now the a value is the a value I just wrote down, 36 over 100. And then I've got 1 minus r, and then the r is 1 over 100. Now, that's definitely not a ratio of integers just yet, but it will lead us to that. So, lots of things we could do. I'm going to multiply by 100 to get rid of all the fractions. So that will give me 36 on top, and 100 minus 1 on bottom. Right, because I'm distributing the 100 through. So 36 over 99. And we want, that is a ratio of integers, but we want it reduced, right? So what will they both divide by? 9, which will give me 4/11. And if you wanted to confirm, just to make sure really that 4/11 is right, of course you could just grab your calculator, type in 4 over 11, and see that the decimal expansion it will spit back out at you is the 0.36 repeating that we began with. So that's pretty cool, right? Interestingly enough, you could actually use this one to also prove if you were less convinced of it than you were already. Hopefully you're convinced that 0.9 repeating is equal to 1. You could do the same thing with that. And you could get to the end and it would tell you it's 1 over 1. So if you've never seen that before, it will work. All right, some properties now. So far, we have yet to see any properties that are unexpected. They do everything that we want them to do, and today will be no different. So this is Theorem 9.7. And these are the properties of infinite series. So we're going to let the summation of AN and the summation of BN be convergent series. And we're going to let capital A, capital B, and we use a lowercase c, just because of what we're working with. Not that it matters, but just for reference, be real numbers. And two more conditions. The summation of A sub n is capital A. The summation of B sub n is capital B. So with those conditions, the following will hold. Then, number 1, if you have the summation from n equal 1 to infinity of c times a sub n. It's going to equal c times a. We saw a very similar statement of this with sequences already in 9.1, and it works as well for series because a series is simply a sequence of partial sums, right? The second one is the summation from n equal 1 to infinity of a sub n plus or minus b sub n. So again, we saw this before, it's going to be a plus or minus b. This isn't anything new, but what it allows us to do is expand the kinds of sequences that we can do summations for very quickly. So we've learned two different types of series, geometric series and the telescoping series. But now we're able to to combine those two ideas into a single one, or to combine them within themselves. So that's actually what this next example is doing. So we're going to determine the convergence or divergence of the series. And the series that we're looking at for this one is the summation from k equals 0 to infinity of 1 over 2 to the k minus 1 over 3. Sorry, that's there. Minus 1 over 3 to the k. And this is not either of the types of sequences, like the pattern inside that we looked at before. But if I can break the apart piece in between the parentheses, right, inside the parentheses, I can make it into sequences we have seen, right, or series we have seen. I'm going to struggle with this sequence series thing for a few days, I'm sorry. Series we have seen. So if I separate this like this, k equals 0 to infinity of 1 over 2 to the k, and the summation from k equals 0 to infinity of 1 over 3 to the k. Now I actually have two series that I do know are geometric, right? What is the common ratio, or the ratio, of this first one, the 1 over 2 to the k? It's 1/2. And what is the ratio of 1 over 3 to the k? It's 1/3. So each of these individually do converge, right? So according to my theorem above, since each of those individually converge, and they will have a limit because they converge, because, you know, that's what it means to converge. And even if we didn't know what it was, we could stop at this point and say this will converge, because each of the individual pieces do. So this converges. Because both pieces are geometrically convergent. Or both pieces geometrically converge, let's say it that way. Both pieces, otherwise I don't have space. Pieces geometric. Both pieces geometrically converge. So since both pieces geometrically converge, this will also converge. Okay, so that's what we've done so far. We aren't asked to do it, but could we find what it converges to? Sure. We would just find what the first one converges to, right? And we'd find what the second one converges to. And according to the theorem up here that we just discussed, 9.7, we would be able to add those two convergent pieces together. Make sense? Okay, so sometimes you might be asked to do that as well. All right, the last piece that we're going to take a look at today, I like it that it shows up in this section because it's a very common misconception that students have, and you will have it at one point during the semester. I'll probably misstate something at one point in the semester, and it's going to hinge back on this too, and you'll be like, wait a minute, didn't you say? And you'll be like, you're right, I did. So let me show you what we're talking about. This is Theorem 9.8. And it actually talks about divergence. Theorem 9.8, 9.9 is actually the convergent one, 9.8 first, is the limit of the nth term. And it says the following: if the summation from n equal 1 to infinity of the sequence a sub n converges, then the limit of the sequence, and I do mean sequence here, the limit of the sequence a sub n must equal 0. Just for an example, so you can think about why this makes sense, think about one of the geometric ones we just did, right? Like 1 over 2 to the k. If you multiply 1 over 2 times 1 over 2 times 1 over 2 times, if you do this indefinitely, that sequence that's inside the summation is going to taper off to 0, right? Yeah, because if you multiply by 1/2, it continues to decrease every single time, but it never becomes negative, it never becomes 0, but it's getting infinitely small, okay? Infinitely small to 0. What this doesn't say is that the reverse is true. Simply knowing that the limit of a sub n of the sequence is 0 does not necessarily mean that the series converges. And that's what the divergence theorem that follows this says. So theorem 9.9 says, okay, so it's called the nth term for divergence. It says if the limit as n goes to infinity of a sub n does not equal 0, then the summation from n equal 1 to infinity of a sub n diverges. Notice what it doesn't say. It doesn't say anything about when anything converges. It only tells you when something diverges. So let's think of just a very simple sequence already that you can know about this, right? Like, so let's say you had a sequence that was 1 plus 1 plus 1 plus 1. Super boring, right? There's no way it's going to converge, right? Its limit is not equal to 0. Clearly, its limit's 1. But it makes sense that it would diverge because you're adding it to itself. You're never going to stop getting bigger, right? If you're adding 1 every time, it never stops getting any larger. So the only chance that you might have for it to actually converge is if you're adding something that's decreasing every time. So if you're adding something that's not decreasing to 0 every time, you stand no chance of convergence. These two statements are actually contrapositives. Contrapositives means that we change the order of the statement around, right? And we negate it at the same time. So this statement right here at the beginning talks about convergence. This one is the negation of that, which is talking about divergence. This statement says it goes to 0. This statement says it does not. So contrapositives switch the order of the direction of the logical statement, and they negate both pieces. So these are contrapositive statements to one another. And let me show you how we actually use this. So determine convergence or divergence. And the example we're going to do is the summation from k equal 1 to infinity of 3k over k plus 4. So when you look at the 3k over the k plus 4, first of all, you should look at that and say it's not geometric, right? You should also say it's not telescoping, because telescoping means I have to have 2 factors in the denominator. So you're left with the only other thing that we've done today, which is the one we just did about divergence. So at best, it's going to be inconclusive or divergent, because the test for divergence cannot tell you it converges. So our answer has to be one of these 2 things at this point. It either diverges or we simply don't know. And what we're going to do is we're going to be basing that on what's happening inside of the summation, specifically to the series. And it's the limit. What I want to know is what is the limit as k goes to infinity of 3k over k plus 4. Well, we spent a whole section, right, 9.1, talking about limits of sequences. That's what this is. How did we deal with 3k over k plus 4, finding its limits? Looked like this. Right? We want each of the pieces, because right now, you could use L'Hopital's rule too if you want to. This actually would fit for L'Hopital's rule, so if you like that better, go for it. But this is the way we did it first. This is our first sort of tool in our tool belt. So the limit is k goes to infinity. On the top, I have 3. On the bottom, I have 1 plus 4 over k. What do I know about the 4 over k? Goes to 0, right? As k goes to infinity, the 4 over k goes to 0. So what does this limit approach? 3. And I know this is not rocket science, but 3 does not equal 0, right? Why does it matter? Well, because the nth test for divergence talks about that limit and whether or not it does or does not equal 0, right? And it does not equal 0. And since it does not equal 0, what that means is this diverges. I'm basically adding things together every single time that are pretty close to 3 eventually, right? If you add 3 to something every time, it's never going to like taper off to a specific value. So this one diverges. And we want to reference why. Every time you're telling me if something converges or diverges, you should be able to tell me why. Why? It's the geometric series. Why? It's a telescoping series. Why? This one is because it's the nth test for divergence. Nth test for divergence. Okay, we do have homework, written homework. The written homework is kind of lengthy because the web-assigned homework is very small, okay? So they're balancing. But the written homework for this, what happened? Oh, I don't think I ever deleted this slide from before. All right, so the homework for this is on page 605. And it's numbers 12, 15, 20, 23, 31, 36, 41, 44, 46, 49, 52, and 56. So again, the web assigned work for this is very brief.